All right, so now we're going to finish up the chapter 2 notes by talking about pH. Before that happens, make sure that you have submitted your water property essays on Google Classroom. And if you aren't sure what the requirements on that were, you can always look at the post where the assignment is. And like I said, we're going to go over pH notes today. The notes themselves aren't actually that long, but there is a demo that follows up so that you get to practice using the information that you learn in the notes. Since we're finishing up chapter 2, after this, I'm going to actually ask y'all to start on your chapter 3 summary and learn smart of the textbook, which means that you got to use your McGraw-Hill site. And that is going to be due the following Wednesday. Okay, so Wednesday of next week. The objective is still the same. Learners will be able to justify the selection of data regarding the types of molecules an animal, plant, or bacterium take in as building blocks or excrete. And again, this is all part of Unit 1. Just a heads up, after after Chapter 3, we're done with Unit 1, which means that we're going to be having a test. So in about another week, we're going to have a test on all of these subjects that we've been talking about so far. So it's always a good idea to look over your notes if you're ever unsure about anything or ask questions. All right, so pH. pH stands for potential hydrogen. And so when water ionizes, it releases an equal amount of hydrogen ions and hydroxide ions. So actually very few molecules are ever ionized or dissociated at a time. And the amount in water at any time is 1 times 10 to the negative 7 moles per liter, which is a really low concentration. Okay, that's in the that's in like the 1 over 10 million. Okay, so that's a very low number. And basically, when you look at water, it's H2O, right? Which means there are 2 hydrogens and 1 oxygen that make up the chemical composition of water. When they dissociate, they dissociate into H plus and OH minus. And that's just how it is. Hydrogens are acidic, hydroxides are basic. So they cancel each other out in charge when you add them together, which is why water is considered a neutral molecule. Now, acids are substances that dissolve in water, dissociate in water. So when you add a powder to a water or add a liquid to a water and it dissociates and releases a lot of H pluses or hydrogen ions, it's an acid. So based on how many hydrogen atoms it releases, it tells you if it's stronger or weaker. So if there's a lot of hydrogen ions released, then it's a stronger acid. And if it releases fewer H's, but it still releases the H pluses, then it's a weaker acid, but it's still on the acidic side, right? A base is a substance that dissociates in water and releases OH minus or hydroxide ions. So the strength is the same as for acids. The more OH ions that the base releases when it's added to water means that it's a stronger base. And if it releases only a little bit of OHs, then it's a weaker base, but it's still basic. It's still not neutral once it starts releasing OHs. So the pH scale, I'll draw for you on the next page, but it indicates acidity or basicity. Another term for basicity was alkalinity, but we don't really use that term anymore. If you've ever heard about it, you think about like Smart Water. They're trying to advertise now that they're selling alkaline water because it balances out the acidity found in the human body. And that's kind of voodoo science. It's not actually true. It just kind of is something that is cool that people want to jump onto because it's a fad. So the pH scale has numbers ranging from 0 to 14. 0 is the most acidic. 14 is the most basic. 7 is neutral. So basically, if you are at 7, then you're neutral. Water is a 7, right? Pure water is a 7 and it's neutral. Anything lower than a 7 is acidic. 6 is weakly acidic, but it's still acidic, right? 8 is basic, a little basic, right? Weakly basic, but it's still basic. If you go all the way up to like 13, 14, that's super basic. Things that are super basic are just as bad as things that are super acidic. They're both corrosive. They can both melt flesh off of bones and give you severe burns, right? So when we work with those things, we're going to be extra careful. Okay, so 7 is neutral, where hydrogen ions and hydroxide ion concentrations are equal, right? Because when you think about it, water, when it breaks apart, it can only break into 1 H and 1 OH at the same time. So whenever water is ionizing, because it's a neutral, it's going to ionize equally. It's going to, whenever it produces one hydrogen, it also produces one hydroxide. And it's always going to produce them in a 1-to-1 ratio when a water molecule breaks apart. Some things, though, they only break apart and release hydrogens, and some things only release OHs or hydroxides, and those determine if you're acidic or basic then. So if you move from 0 to 14, each individual increment is 10 times more basic. So we're not saying that, oh, if you are neutral, if you have water and it's neutral, and then you have orange juice and it's a 9, it's a 6 for basicness. If it's a 6 for acidity, right, then it's not just 1 times more acidic, right? We know orange juice is sour, but it's more than 1 times as sour as water, right? It's going to be 10 times as sour because you jumped 1 on the scale. So think of each number as an exponent on the pH scale and not actually just as a basic number. Buffers are chemicals or combinations of chemicals that keep the pH within normal limits. So for example, our healthy blood pH is a little bit basic. It's a 7.4, and it has some carbonic acid in it because carbonic acids will react with water and produce OHs to balance out other things that get added into it that are like carbon dioxide and oxygen that cause blood to become more acidic. So you can't just let your blood get more and more acidic as more and more carbon dioxide builds into it, right? So carbonic acid will help react with the water in your blood to make sure that it's also producing OHs that then react with the H's floating around to turn back into water. So it keeps the pH level, because if your blood gets too acidic, you die from blood poisoning. And if your blood gets too basic, you also die from blood poisoning. So maintaining this kind of equilibrium in pH of your blood is super important for survival. So this is the pH scale. Now again, we go from 0 all the way over to 14, right? 14 is 10 times more basic than 13. That's what we just talked about. You can't see the 1 over here. Let me draw that in. So 14 is actually 10 times more basic than 13. It's not just 1 times increase. It's a 10-fold increase between each number. So if you're comparing a 7 to a 10, right? That's 10, 100, 1,000. So a 10 is 1,000 times more basic than a 7 is. It's not just three more basic. It's not 10 minus 7, okay? So again, 7 is neutral. That's where water kind of sits. Orange juice can go down to close around 4. We usually find it around 5 or 6 if it's something that we are consuming and it has preservatives in it and sugars in it. And then strong acids like stomach acid can go all the way down to 1 or 0, right? If you think about it, the stomach acid, for example, like in dogs, can literally dissolve bones. They're very, very, very acidic and they're corrosive. Okay, so if it was anywhere outside of your stomach, it would actually damage your body. On the other side here, we have things that are basic. Tums fall between the 9 and the 10, right? You eat Tums when you have acid reflux and you feel nauseous and you feel the burning in your esophagus because it feels like you are puking or you're going to puke and you feel your stomach acid burning. You can take Tums to kind of counteract that because they're basic. So they'll react with the acids and produce water when the H's from the acid add with the OHs produced by the Tums. Now, if you go to the super, super strong base side, you can get things like drain cleaner. Concentrated bleach is also very, very basic. And those things are all dangerous to come directly in contact with. So if we ever work with them in lab, when we go back in person, then we're going to be wearing protective gear like gloves and aprons to make sure that they don't get on us and our skin because it can actually burn you. So here is actually how you calculate pH. And it's kind of interesting because, like I said before, we're working on a log scale, which means those numbers that you were talking about before with 0 all the way to 14, those are actually exponents. So again, water ionizes to a concentration of 1 times 10 to the negative 7. And that means that this 7 is the number 7 that we see on the pH scale. Because 1 times 10 to the negative 7 is actually, you can invert it because there's a negative here, right? So if you invert it to get rid of the negative, it becomes 1 over 1 times 10 to the 7 power. And that equals 1 over 10 million, right? 1, 2, 3, 4, 5, 6, and then 10 more. So 1 over 10 million. When you change that into a decimal form, that tells you how many hydrogen ions water is producing in a liter of water. So if you have a liter container of water that you were, for example, drinking, like, for example, like my water bottle right here is a liter. That means inside of this liter, there is 0.0000001 hydrogen ions in here. Okay, and at that concentration, it doesn't really affect us because it's neutral and it's really, really low concentration. So we use a log base to transform these difficult to work with numbers, because if you're just talking about all these zeros all the time, then it's actually really, really hard to like write out every single time and then also explain and make sure that you're speaking the right number of zeros each time. So we changed it to an easier scale of 0 to 14, right? So when you negative log function on your calculator and you negative log the 1 times 10 to the negative 7, when the 7 moves to the front during the log function, because that's how exponents move, the negatives actually cancel out in the front, so you don't have to worry about those. That's why it's okay that it's negative here. And then 1 times 10 on a log base is 10, right? But 10 to the 10 is just 1, right? So log base is 10 as the base down here. And 10 to the what power is 10? 10 raised to what power is 10? 10 to the 1 power is 10. So if you have negative times negative 7 times 1, that's just going to end up equaling to 7. Okay, so this is where we got the 7 that indicates water's H plus or hydrogen ion concentration, aka its acidity on the pH scale. Here's some comparisons now. So if you compare a pH of 0, which is a super, super strong acid, right? A concentration of H plus is 1 times 10 to the negative 0. That means the same thing as just 10 to the 0, which is 1 times 1, because 10 to the power of 0, any number to the power of 0 is just 1. That means you have 1 molar H plus per liter of water. That basically means that this whole thing is made up of hydrogen ions, and this whole thing is just pure acid, as strong as it gets. That's a lot of H plus ions. It's super, super, super concentrated in a potential hydrogen scale. And we just talked about water, right? pH of 7 is neutral. When you move it all the way down and you move the 7 down to the bottom, you get 0.0000001 molar concentration of hydrogen ions. So that's our medium amount, right? It's our normal amount that we experience in life, in living organisms on Earth, and that's neutral. On the other hand, if we calculate a strong base, it's a pH of 14. So 1 times 10 to the negative 14 concentration of hydrogen ions is actually going to be about 0.13 zeros and 1 molar concentration of hydrogen ions. The reason why this number is super, super low is because we didn't use an OH scale, right? This is still talking about hydrogen ions, and we know that bases don't actually produce many hydrogen ions. They're the ones that produce hydroxide or OH minus ions, right? So if you produce very, very few hydrogen ions, it's because you're probably producing more OH minus ions. Okay. We also have a pOH scale, which means that the higher number of pOH is more acidic and the lower number of pOH is more basic. But we actually just use the pH reference tool because hydrogen ions are much more commonly found in most life forms, and we deal mostly on the acidic side for a lot of things. So it's easier just to choose one scale and stick to it. And so scientists just chose the pH scale instead of the pOH scale, just because the application is more broad. So you guys are going to watch a demo video in one of the following posts on Google Classroom. And while you watch the demo, do the following steps for every single solution. We're testing probably around like 8 or 9 solutions that I'm going to be showing and testing for you. And you're going to be making visual observations and then calculations based off of those. So the first thing for each solution that I introduce, for example, if I say this first one we're testing is going to be milk, you're going to write down the name of the solution and then predict what pH you think it will be. Any number between 0 and 14. If you're not sure, just make a guess. It's okay. For the second part for each solution, record the actual pH. So I'm going to actually use a special pH test strip that reacts and changes color based on the pH of the solution. So I'll dip it in there and compare it to the little comparison picture for you, and you'll get to see what it is, and you're going to record the actual pH based on the test strip color down. And it's kind of interesting to see what the reality is versus what you thought it was initially. Third thing, you're going to write the H plus concentration based on the pH you find. So remember, you're going to go back and calculate pH of 7 and how it becomes a hydrogen concentration of 1 times 10 to the negative 7, right? Because the 7 is the exact negative exponent that goes on top of the 1 times 10 to the whatever, okay? It's pretty simple. You're just converting the pH number to the exponent and making it negative. Then 4, you're going to include how many times more basic than water the solution is. So we're going to compare everything to water. Remember, when you're jumping from water, which is a 7, up to an 8, that's 10 times more basic. It's not 1 times more basic, it's 10 times more basic, right? So if you have the water being a pH of 7, and for example, hand soap being a pH of 9, therefore you're jumping 2 times, right? So you're jumping 7 to 8, 8 to 9, and each time is 10. So you're going to jump 10 and then 10. So 10 to the power of 2 is 100, right? 10 and then 10, you're jumping 10 times 10, which is 100. So therefore, hand soap is 100 times more basic than water. And you're just writing that for the fourth part of each solution, right? So that's a follow-up that'll be due at the end of the day. And then don't forget that your chapter 3 summary is going to be due on the Wednesday of the following week. So you have a little less than a week, but there's also a weekend built into there. So don't leave it to the last second, because you're going to want time to go over material and kind of refresh yourself before we actually start reviewing for the exam.